In 1991, a single volcanic eruption cooled the Earth and transformed sunsets around the globe. Today, some scientists are preparing to mimic that event on purpose by injecting reflective particles into the stratosphere. They promise stratospheric aerosol injection could slow climate change. But what if this human experiment triggers unseen consequences we can't control? Here's what the world needs to consider before the first particle leaves the ground. Stratospheric aerosol injection begins with a simple engineered idea: brighten the planet's skies to cool its surface. Scientists propose releasing tiny reflective particles, often sulfates, directly into the stratosphere, a layer of atmosphere starting about 10 miles above our heads. The goal is to increase Earth's albedo, or reflectivity, so more sunlight bounces back into space, lowering global temperatures. But this isn't a one-time fix. To keep the cooling effect, fleets of specially designed aircraft or high-altitude balloons would need to carry out thousands of flights each year, dispersing new particles as older ones settle out. David Keith, a leading voice in geoengineering research, argues that only through careful, transparent experimentation can we understand the true risks and benefits. Unlike a passing volcanic plume, stratospheric aerosol injection would demand an ongoing planetary-scale commitment, an engineered climate system that must be actively maintained to work. In June 1991, Mount Pinatubo erupted in the Philippines, sending nearly 20 million tons of sulfur dioxide high into the stratosphere. Within weeks, a thin veil of sulfate aerosols wrapped around the globe, scattering sunlight and transforming sunsets into brilliant shades of purple and orange. Satellite data and ground measurements confirmed a measurable effect. Earth's average temperature dropped by about half a degree Celsius, roughly 0.4 to 0.6 degrees Celsius, over the next year. The cooling lasted nearly 2 years, making Pinatubo the largest volcanic climate event of the 20th century. The eruption also increased the atmosphere's optical depth, dimming sunlight and subtly shifting the color of the sky in cities thousands of miles away. For scientists, Pinatubo offered an unplanned, full-scale test of the very process at the heart of stratospheric aerosol injection. It proved that injecting particles into the upper atmosphere could rapidly cool the planet and alter the look of the sky, turning theory into observable reality. Climate models consistently show that stratospheric aerosol injection could deliver a substantial drop in global temperatures. Under high-emission scenarios, simulations project a reduction in global mean temperature of 1 to 2 degrees Celsius within a decade of sustained deployment. These ensemble model results, often visualized as global maps, reveal a pronounced cooling effect across much of the planet's surface. The magnitude rivals or even exceeds the cooling observed after Mount Pinatubo's eruption, but on a controlled, ongoing basis. This modeled benefit stands out as a rare instance where a single intervention could rapidly offset decades of warming, at least in terms of global averages. Rainfall patterns do not respond evenly to a cooler planet. Climate models from the Geopolitical project show that stratospheric aerosol injection could weaken the South Asian monsoon, reducing summer rainfall over India and Bangladesh. Alan Robach, a leading monsoon researcher, warns that even a modest decline in monsoon strength could threaten food security for hundreds of millions. In Bihar, rice farmers wait for the first rains to plant their fields. If the monsoon falters, entire communities risk losing both harvest and income. Across the Sahel, projections reveal a patchwork of outcomes, some years wetter, others drier, but always more unpredictable. The burden falls hardest on those least able to adapt. Above the clouds, stratospheric aerosols become more than just sunlight reflectors. Their surfaces act as chemical workbenches, accelerating reactions that strip ozone from the upper atmosphere. When sulfate particles spread across the stratosphere, they provide a platform for chlorine and bromine compounds to break down ozone molecules at a much faster rate. As ozone thins, more ultraviolet radiation reaches the ground. Model projections warn that under high-burden scenarios, surface UV levels could rise enough to threaten crops, ecosystems, and human health. The very particles intended to shield the planet from heat may leave it exposed to a different, invisible danger. Ending stratospheric aerosol injection isn't as simple as flipping a switch. Ken Caldera, a leading climate modeler, warns that the most severe risk comes if the program stops suddenly. In that case, global temperatures could surge by as much as 1 to 4 degrees Celsius within just 5 years, a pace far beyond anything in recorded history. The climate system, held in check by years of reflective particles, would snap back violently to the reality of accumulated greenhouse gases. This rapid warming would outpace the ability of crops, ecosystems, and entire societies to adapt, leaving little time for response or recovery. No international treaty governs stratospheric aerosol injection. There are no binding safeguards, no global liability rules, and no agreed process for monitoring or enforcement. The SRMGI warns that, without oversight, decisions about the planet's atmosphere could be made by a handful of actors, not the world as a whole. In 1991, Mount Pinatubo's eruption lowered global temperatures by up to 0.6 degrees Celsius for nearly 2 years, proof that stratospheric aerosols can cool the planet. Today, models show that deliberate stratospheric aerosol injection could deliver similar global cooling. Yet these same studies reveal sharp regional risks, from weakened monsoon rains to increased droughts in the soil. Chemical analysis confirms that added particles may speed up ozone depletion, raising surface UV levels. Despite decades of research, no international treaty governs the use of SAI, and termination could trigger a sudden global temperature spike within 5 years. Key decisions, including who controls deployment and monitoring, remain unresolved. While the science demonstrates what is possible, the long-term consequences, political, environmental, and ethical, are still unclear. For now, stratospheric aerosol injection remains a powerful but deeply uncertain tool at the edge of climate policy.